So we're going to talk about properties of covariance, which is pretty important. If you don't know the definition of covariance, then here it is. Covariance of x and y is equal to expectation of x times y minus expectation of x times expectation of y. From now on, I'm going to say E for expectation. Usually x and y are random variables, but as you can see from this property 0 here, we can have a constant instead. So we're going to show four properties of covariance. The first property is that the covariance of a constant and x, a random variable, is equal to 0. So this constant a is going to be in the real number. The second property is the symmetry property of covariance. So cov of x and y is equal to cov of y and x. This property 2 is a linearity property of covariance. So a is a constant, and covariance of ax and y is equal to cov x and ay, which is also equal to a times covariance of x and y. And property 3, this is another linearity property of covariance. Cov of x and y plus z is equal to cov of xy plus cov of xz. Now, we'll do a short proof of property 3 star here. If you look at property 3, from property 1 we have that covariance of x and y is equal to covariance of y and x. So we can get that from the property 1 over here. Covariance of x and z is equal to covariance of z and x. And you get that again from property 1. And covariance of x and y plus z is equal to cov of y plus z and x. Again from property 1. So if property 3 is true, then this implies that property 3 star is true, provided that property 1 is true, which we'll show. So property 0, the covariance of a constant and x is 0. So you just apply the definition of covariance here, right? So we have E of a and x minus E of a and E of x. And by linearity of expectation, we can pull out this constant. So it becomes a times E of x. And the expectation of a constant is just the constant itself, because there's no randomness in a constant. So this becomes a times E of x, which you can see this is 0. So property 0 is proven. Now for the symmetry property. So we want to show covariance of x and y is equal to covariance of y and x. Again, we just apply the definition of covariance. So this first line is straight from the definition of covariance. Now note that you can switch the order of x and y. It doesn't matter. So this becomes E of x and y is the same thing as E of y and x. Now we can switch the order of the products. E of x times E of y is E of y times E of x. But this is just covariance of y and x by reverse applying the definition of covariance. So property 1 is proven. Property 2, covariance of a, x, and y. So we'll first show this first equality over here. So apply the definition of covariance again to this random variable ax and this random variable y. So this is E of axy minus E of ax times E of y. Now again, we can apply linearity to the random variable xy. So a is a constant, so we can pull this out. And we can apply linearity and pull out this constant here. So we get a's on both terms. And we can see that we can factor out an a from both terms over here. So this becomes a times E of xy minus E of x times E of y. But this is just the definition of covariance. And then, so this proves the first equality. Now for the second equality, we have, again, covariance of AXY, the covariance of AX and Y is equal to A times covariance of X and Y. This follows from what we just showed over here. And then this is equal to A times covariance of Y and X. This follows from property 1, which we showed. So covariance of X and Y is equal to covariance of Y and X. Now we can reverse apply this property that we showed over here to this and get that A times covariance of Y and X is equal to covariance of AY and X. Now again, we can apply property 1 to switch the order of these. So covariance of AY and X is equal to covariance of X and AY. So this shows the second equality. You can do a bunch of these orders. I'm just showing some things that might confuse you, but you can figure out most of these covariance identities for yourself. So proof 3. So 3 is again the linearity, another part of the linearity property of covariance. So we want to show covariance of X and Y plus Z is equal to covariance of X and Y plus covariance of X and Z. So again, we just apply the definition of covariance, right? So we have E of X and Y plus Z minus E of X times E of Y plus Z. And here we apply the distributive property. So this becomes E of XY plus XZ. And we apply the linearity property here. So for any two random variables, we have E of Y plus Z is equal to E of Y plus E of Z. And here we apply the linearity property to these two random variables to get that E of XY plus XZ is equal to E of XY plus E of XZ. And we just apply the distributive property here with E of X. So this becomes minus E of X times E of Y minus E of X times E of Z. So note that these two together form covariance of X and Y, and these two together form covariance of X and Z. So this proves property 3. Oops, this proves property 3. Now we want to show some properties of variance, and you can do these pretty easily from the covariance identities. So that's why we wanted to prove the covariance identities, because these variance identities are pretty easy to show from the ones that we just proved above. So if you forgot the definition of variance, then there are two that you can use. One is that variance of X is equal to expectation of X minus E of X, the quantity squared. And then another definition is that variance of X is the second moment minus the square of the first moment. So this identity, variance is non-negative. And this is pretty easy to show because if you look at this first definition of variance, then we have E of X minus expectation of X squared. And you see that this random variable here, it's non-negative because you're squaring something. So the square of any number is non-negative, 0 squared is 0, but any other number, you're going to get something positive, right? So this quantity is non-negative, which implies that the expectation of that non-negative quantity is non-negative. And this you can show from monotonicity. Right. Now the first property is that variance of X plus a constant A is equal to variance of X. And the second property is that variance of A and X is equal to A squared times variance of X. Okay, so I guess, yeah, proof of 0. So we explained that before. Now, proof of 1, we have variance of X plus A. By definition of variance and by definition of covariance, So you can check this for yourself. Variance of x plus a is actually equal to covariance of x plus a and x plus a. And using the above covariance identities, we can show that this is covariance of x and x plus 2 times covariance of a and x plus covariance of a and a. So you can use properties 0, 3, and 1, yes. But covariance of a and x is 0. Covariance of a and a is also 0. So all that remains is covariance of x and x, which again, by definition of variance and covariance, is variance of x. Now, proof of 2. Variance of a times x is equal to, by definition of variance again, is equal to covariance of ax and ax. By applying the linearity property of covariance, we can pull out an a from both ax and ax. So this becomes a squared covariance of x and x. But again, by applying the definition of variance, covariance of x and x is variance of x. So we showed the second property as well. So this is a good exercise for you to get familiar with the properties of covariance. So you should try to prove this, and I think this is true. So good luck with that.